All right. Okay now. All right. Okay. So I repeat again. Okay. So this is the second half of the semester. All right. Okay. Nanti ada student masuk. Alright. Okay. Tadi boleh dengar suara kan? Okay, never mind. Okay, so we look at the integration. Okay, so as I mentioned just now, okay, so let's say you want to integrate from 0 to 1 x dx. Okay, so this is very simple integration. You should know that you have x squared over 2. Okay, evaluate from 0 to 1, so the answer should be 1 over 2. Okay, so what if now I have another very complex function such as sine x over x, and I want to evaluate, let's say, from 2 to 3, let's say. Okay, so we might facing the problems how to integrate the sine x over x here. Okay, where these functions can be integrated by using the L'Hopital rule. Okay, so this is one of the reasons why we need to learn for the numerical integration. So if for the simple function like this, I think you have no problem to do for the integration by using the calculus. However, if we have very complex functions like this, so we might be facing the problem how to get the integration of such complex function. Okay, so if we do not know how to integrate it analytically, so we can seek for the help of the numerical methods. So this is the first reason why we need to learn for the numerical methods, numerical integrations. Okay, so the second reason is that if you have the t, okay, so maybe now I have the acceleration here, okay, at different instances. Okay, so I know that if I want to get the velocity, I need to integrate the acceleration, right? Okay. If you want to apply the knowledge in calculus, you need to know that what is this function, the AT. But however, at some occasions, you only have a set of data point here, the tabular data. Okay, so it doesn't mean that if you do not know what's the functions here, you cannot do the integration. Okay, so we still can integrate the data if we know how to make use of the numerical methods. Okay, so this is the second reason why we need to have some extra knowledge for the numerical integration instead by using the calculus. Because if you want to make use of the calculus knowledge, you need to know that what is actually this function is the AT. Either it is, let's say, t squared plus 1, then only you can perform the numerical, you can perform the integration. Okay, so this is the reason that we want to learn for the numerical methods for the integration. All right. Okay, so this is the outline for chapter 6. Okay, so we have symptoms 1 over 3 and 3 over 8. So before we proceed to the symptoms 1 over 3 and 3 over 8, we will have two extra methods, which is the rectangular rule and also the trapezoidal rule. Okay, then only we will proceed to the symptoms 1 over 3 and symptoms 3 over 8. And also we have the Gauss quadrature. So you can have 4 points, 5 points Gauss quadrature, but we only will look at the 2 points and also the 3 points. But once you know how to solve for the 2 and 3 points, you should have no problems in order to solve the integration by using 4 points, or you can even using the 6-point Gauss quadrature in this case. Okay, so as usual, let us look at the topic learning outcome. Okay, so for the topic learning outcome, okay, so no matter you have a function, so let's say you have been given y(x) equals to x squared over square root x plus 1. Okay, or you have been given with a set of data points, so which is in the table form. Let's say you have the TAT here. Okay, so either you know the function or you have a set of data points, so you should be able to apply any of the numerical methods, either Simpson's or the Gauss quadrature, or using the trapezoidal rule to find the integration. And also for the second learning outcome, you should, this is for the Simpson methods. Okay, so for the Simpson's methods, we have two types of the Simpsons. So one is 1/3, and another is Simpson's 3/8. So you should know that there is some requirement for us to choose when we want to use the Simpson's 1/3 and when to apply the Simpson's 3/8. It is actually depends on the number of data points that we have. So we will look at it later in today's class. Okay, so this is the learning outcome. Okay, so now let us look at what is actually the integration. All right. Okay, so before we proceed to here, okay, so let us consider one simple example here. So if I want to evaluate 0 to 1 as ds, right? Okay, so previously you know that the answer is 1/2, right? Okay, but actually what is integration of x from 0 to 1? Okay, so if I try to illustrate this, okay, so this is the function yx equals to x, right? Okay, so I have yx equals to x here. Okay, so if I plot for the graph, so you should know that this is the function yx equals to x. Okay, then I have the lower bound of integration from 0 to 1. Okay, so meaning that 0 and until 1 here, let's say. Right? Okay, so now let me do some shading here. Okay, so let us see actually what is this. Right. Okay, so if x is 1, so this is y equals to x, so which means that the height here is 1, right? Okay, because this is the function y equals to x here, so x is 1, y is 1. Okay, so if I try to find the area of region here, you know that this is a straight triangle. So I know that the area of here is 1/2 the base multiplied with the height, right? So the base is 1 unit and the height here also 1 unit. Okay, and the answer is 1/2. Okay, so now we can actually relate the relationship between the area of the region with the integration, right? Where you see that if you try to integrate x from 0 to 1, you get the answer of 1/2. So this is actually equivalent that you find for the region of the area here, which is bounded by the functions yx, which y equals to x, bounded by the line x equal to 0, and bounded by the line x equals to 1, and also the x-axis. Okay, so you also get 1/2. So in general way, we will say that if we try to find for the integration of a function within the lower bound and the upper bound, okay, it is equivalent that we find the area of regions here. Okay, so for this, I show this simple example for you to see that actually what is integration here. Okay, when you try to perform the integration, you are actually trying to find for the area of region here. Right? Okay, so let us put it in a general way. Okay, so generally, we say that the area of region bounded by the y-axis, okay, the x-axis, okay, x equals to x naught and x equals to xn, can be calculated actually by using the area of the region. Okay, so let me illustrate this. Okay, so let's say this is the function y(x). Okay, so previous example, I give you y equals to x. Okay, and bounded by x equals to x naught here. So previous example, we are actually solving 0 to 1 x dx, right? Okay, so this is the y(x). This is x naught. Okay, and this is xn. Okay, so I have x equals to xn here. Okay, so, and I also have the x-axis here. So this is the x-axis. Okay, so the area of region bounded by y(x), x-axis, okay, x equals to x naught, and x equals to xn. Okay, so the area of region here. Okay, so this is actually can be calculated by using integration of the function y(x) with respect to the x from the x naught to xn. Okay, so this is the relationship between the area of region and the integration. Right. Okay, so the relationship between the area of region and the integration is very useful if we have a very complex y-axis here. Right. So, because sometimes you don't know how to find for the integration for the complex function. So in such a case that we can try to calculate the area bounded by this region. Okay, so the first example, the first numerical that we will look at is the rectangular rule. Okay, where we try to use the rectangles to approximate this area. Okay. So we want to approximate the area of region here by using the rectangles. Okay, so let us look at the first numerical methods, which is the rectangular rule. Right. Okay, so now consider that this is the function y(x), right? Okay, then we try to approximate this region. Okay, so this is the similar figures where as this, right? Okay, so now we try to approximate this region by using 3 rectangles here. And you need to note that this rectangle, they have the same width, okay, where we name it as h here. Right. Okay, so in this case, we just make use of this of 3 rectangles, okay? And the starting point, we name it as S0. Then you proceed to x1, x2, and x3, where you should know that x1 is S0 plus h, and x2 is S1 plus h, and so on. So they have the same width for the length, for the width of each rectangle, right? Okay, so previously we know that if we want to integrate the function of y(x) dx, okay, so from x0 to xn, okay, so this is actually, we try to find for the area of region, okay, which is bounded by the y(x) here, okay, x equals to x0 here, okay, x equal to xn here, and also the x-axis. So now we want to find the area of region here. So the first approximation that we are using here is by using 3 rectangles, right? Okay, so I know that I can get this approximation by sum out the area 1, okay, area 2, and also area 3. Okay, so what is the equation for the area of a rectangle? Okay, so luas segi 4 tepat, you should know that it is the panjang kali lebar. Okay, the width multiplied with the height. Okay, so the width here, lebar, is h, right? Okay, so how about the height of the area 1? So you know that the height here is y0, right? So you have hy0. Okay, so how about the area of the region for the area 2 here? So the width is h and the height is here. Okay, so which is y1. Okay, so the same thing applied for the area 3. So you have the width as h and the height as y2. So you have hy2. Right. Okay, but how you think about the accuracy here? The accuracy of your approximations here. Okay, so we want to approximate the area bounded over here, right? Okay, if I only make use of these 3 triangles, I will see that there are still some region that we miss out here. Okay, where the rectangulars does not cover this area. Right, so which means that the approximations here by using the area here is not that accurate, because the more area we can cover here, so means the accuracy is better. Okay, so one of the possible solution, we use smaller step size. Okay, so I will show you if we make use of the smaller step size, so the approximation answer that we get will look better here. Okay, so let us look at the simulations here. Right. Okay, so let's say I want to integrate the function of negative 3x squared plus 10 from 0 to 1 here. Okay, so you should know that we are actually trying to find for the area of region here below the function fx bounded by x equals to 0, x equal to 1, and also the x-axis. We want to find the area here. Okay, so this is by using the rectangular rule, where I try to approximate it by using 3 rectangles. Okay, so where you can see that there's some missing region here. Right. And this is by using 3 rectangles. So now let me increase it by using, let's say, 10 rectangles here. Right. Okay, so this is the answer by using 10 rectangles, where you will see that the approximations here improve, but there are still some white spaces here. Right. Okay, so now let us increase to, let's say, 30 rectangles. Okay, you will see that the answers are even better. Okay, but there are still some white spaces here. Okay, so we can increase, let's say I use 300 rectangles here. All right, so look better, right? Okay, so this gives us the idea, if we want to have better approximation, we can increase the number of rectangles. So meaning that we use smaller step size. All right. Okay, so this is the possible solutions for us in order to improve the approximations to get the area of region here, where we use smaller step size here. Okay, so this is the idea where how can we find the integration by using the rectangles to approximate the area of regions here. Okay, so let us go for the rectangular rule in a more general way. Okay, so let's say now we use n divisions. Okay, we try to approximate the area of regions here by using n divisions. Okay, so this is rectangular rules. So the divisions here means we use n rectangles. Okay, or sometimes we have the terms n segments. Okay, so divisions or segments are the same. Okay, so we try to divide it into n divisions or n segments here, meaning that you will have n rectangles here. All right. Okay, so you have n rectangles here. Okay, A1, A2 until the AN. Okay, AN here. Right. And the width of the rectangles is calculated by using the lower bound, okay, the upper bound, the xn here, okay, minus the lower bound, the s naught here, okay, and divide by how many rectangles or how many segments that you are using. Okay, so this is the equation that we use to calculate the width of the rectangle here. Okay, so choosing the number of divisions or number of segments here, we need to perform it in a very smart way. Right. Okay, so now let us try to derive the equations for the rectangular rule. Okay, so I know that if I want to carry out the integration from x naught, okay, from s naught, okay, to xn for the function yx dx. Okay, I know that this is actually trying to find for the area of region here. Okay, and now we already decided in order to find for the area of region here by using n rectangles. Okay, so now let us sum up the area of these n rectangles. So I will have the area of first rectangle sum up with the second rectangle until sum up with the n rectangles here. Right? Okay, so now let us look at what is the area of the first rectangle here. Okay, so you know that the area of the rectangle is obtained by using width multiplied with the height, right? So the width is h. Okay, so you have h, and the height is y naught, right? Okay, so you have the width as h, and the height here is y naught, so you have hy naught. Okay, so this is for the first rectangle. Okay, so for the second rectangle, the width is h, and the height here is y1. Okay, so meaning that the area of the second rectangle can be obtained by using h, y1. Okay, so we repeat the same thing until the last rectangle here. Okay, so the last rectangle, width is h, and the height here is yn minus 1. Okay, so this is point xn minus 1. So the corresponding value of the y here is yn minus 1. Okay, so this is point yn, so the corresponding of this point is yn, but for this point is yn. Okay, this point is yn, but we are interested in this point, so this is yn minus 1. Okay, so you should have yn minus 1, the second last point. Okay, so maybe we want to tidy up a little bit. Okay, so I factor out the h. Okay, so inside the bracket, I only have h naught plus h1 until Okay, sorry, y0 plus y1 until yn minus 1. Okay, so this is the equation for rectangular rule. All right. Okay, so now let us proceed to trapezoidal rule. Right. Okay, so maybe you can imagine that for the rectangular rule, we try to approximate the area here by using rectangles. Okay, so now we have the trapezoidal rule. So means that we are trying to approximate the area here by using some trapeziums here. Right. Okay, so refresh a little bit. What is the equations for us to find for the area of region if I have a trapezium here? Okay, so let's say the height here is h. Okay, the length here is a. Okay, and the length here is b. Okay, so you should know that the area of the trapezium is actually 1/2 h. Then you sum up a plus b. Okay, I hope that you still can able to recall the formula. How can we find the area of a trapezium? Okay, so this is the equation that we will use 1/2 h multiplied to the summation of a plus b here. So a is the length here and b is the length over here. All right. Okay, so we will make use of the equations to find for the area of the trapezium in order for us to derive the formula for the trapezoidal rule. Right. Okay, so let us go back to this slide. Right. Okay, so now we know that if I want to find for the integration from s0 to xn for the function ys dx. Okay, so this is equivalent that we find what is the area of region bounded by the ys here. Okay, x equals to x0 here, x equals to xn here, and also the x-axis, right? So we have looked at it at the very beginning. Okay, so now we try to approximate this entire region by using n trapeziums. Okay, so similarly, we divide this into n divisions or n segments, or since we are dealing with the trapezoidal rule, so meaning that we are divided it into n trapeziums. Okay, and again, the width of each or you can consider that this is the height of each trapezium is the same. So we use fixed value for each height of the trapezium. So the h is calculated by using the upper bound minus with the lower bound of your integration and divide by the n. So the n depends on how many segments or how many divisions or how many trapeziums you want to use. Okay, so n you can determine by yourself if it does not been stated in the question. Right? Okay, so we go back to here. We know that the relationship between the integration and the area of region is like this. Okay, so now we try to approximate the area of region by using n trapeziums. All right, so meaning that I need to sum up the area 1, area 2, okay, until the area n here. Okay, so I use the capital N here, area n. All right, okay, so now let us look at the equations for the area 1. All right, okay, so you can observe here, this is actually a trapezium, right? Okay, so this is a trapezium. Okay, so recall back to the equations for the trapeziums. Okay, so you should have 1 over 2 h, the height here. So the height here, okay, so maybe I draw it here. If this is h, this is a, and this is b, so the area of the trapezium is given by 1 over 2 h a plus b. Right? Okay, so now you just try to shift this negative 90 degrees. Okay, so now we get this. Okay, so for the area of the trapeziums here, so referring to the equations here, you should know that the area of the first trapezium can be obtained by 1 over 2, the height here. Okay, so we have the fixed width here, so which is h. Okay, multiplied to the summation of here. So this is your A, and this is your B. Okay, so this point, the value is given by y0, right? Okay, and for this point, okay, the value is given by the y1. Right, so you have y0 plus y1. Right, so this is only for the first trapezium. Okay, so let us look at the second trapezium here. Okay, so again, I have plus, okay, 1 over 2, the height here, so which is h, okay, and sum up the A and the B here. Okay, so the length of the A here is this point, so which is y1. Okay, so the length of the B here, so I know that this is actually x2, so the length of the B here is actually y2, so I have y1 plus y2. Okay, and sum up until the last trapezium. So let us look at the last trapeziums here. Okay, so you should have 1 over 2 h here. Okay, so this is the A. Okay, so the A here will take the value of yn minus 1. And this is the B here. Okay, so the B here will take the value of, this is xn, so this shall be yn. Okay, so plus yn. All right. Okay, but however, we still can do some simplifications here to the equations that we obtain here. Okay, so let me put some shapes over here. Right? Okay, so I continue from here. Okay. So I will see that I have the common factor 1 over 2h, right? So let's say I factor it out, 1 over 2h. Okay. So inside here I have y0 plus y1 plus y1 plus y2 plus until yn minus 1 plus yn. All right, so I factor out the 1 over 2h. Okay, and if you observe here, you see that you have y1 plus y1. Okay, and here you also will have y2 plus y2 if you plus the area of trapeziums for the third trapezium. Okay, and also here you will see that you will have yn minus 1 plus yn minus 1 if you consider the second last trapeziums here. All right. Okay, so at here I will see that I can actually have a more simplified form, 1 over 2h y0 plus 2y1 plus 2y2 plus until 2yn minus 1 plus yn. All right. Okay, and I can even simplify it further. Okay, so I will have 1 over 2h. Okay, y naught, yn, the starting point and the ending point. Okay, I put them together. Okay, so inside here, this is the intermediate value between the y naught and yn. And I see that they have the same constant coefficients 2 here. Okay, so I can have a 2 here. And I have y1, y2 until yn minus 1, right? So I can use the summation form for the yi. And my I start from 1 until n minus 1. Okay, so I can have the most simplified equations for the trapezoidal form, for the trapezoidal rule in this equation. So this is the equation that we will use for the trapezoidal rule. All right. Okay. So let us proceed to the Simpson's 1 over 3 and Simpson's 3 over 8 rule now. Okay, so we just go for the Simpson's 1 over 3 rule. Right. Okay, I will say that the Simpson's 1 over 3 rule. Okay, so if you refer back to the rectangular rule, right? Okay, the rectangular rule. Okay, let us only consider that we try to approximate the region by using one rectangles. Okay. So this is S0 and this is Sn. Okay, and also we look at the trapezoidal rule. Okay, so we try to approximate this region by using the trapezium. Okay, so this is the S0 and this is the Sn. Okay, so if you observe here, the line that we use here actually is a straight line. Okay, so this one is a straight line here. Okay, and this one also a straight line. So meaning that for both rectangular rule, so this is the rectangular rule, and also for the trapezoidal rule. Okay, we are trying to do the approximations here, okay, by using the linear approximation. Okay, in which you try to approximate the error here by using a straight line. Okay, so this one also by using a straight line, a linear approximation. Okay, so linear approximations. So if you have, if you still remember for the chapter 4, linear approximation is the first order polynomial, right? Okay. So for the Simpson's 1 over 3 rule, we are not going to use for, we are going to use higher order of polynomial. So for the Simpsons of, let me see. All right. Okay. So for the Simpsons of 1 over 3 rule, we try to approximate it by using the second order polynomial. Right. Okay. So recall back for the second order polynomial, we need to have 3 points, right? Only you can conduct the second order polynomial. Okay, so for the basic block for the rectangular rule and the trapezoidal rule, okay, the basic block is either 1 rectangles or 1 trapeziums. Whereas for the Simpson's 1 over 3 rules, since we need to have 3 points in order to form a second order polynomial, Okay, so the basic block for us to do the approximations will like this, because you have 3 points. So let me name this as x0, this is x1, and this is x2. Okay, so you have the points y0 here. Okay, so this is for the point y1, and this is point y2. Okay, so means that you will fit a second order polynomial. Okay, so let's say the second order polynomial, okay, look like this. Okay, so this is the second order polynomial that you try to approximate, you use to approximate the area here. Okay, and if Simpson's 1/3 rule, it uses a second order polynomial. So meaning that for the second order polynomial, you need to have 3 points. And if you look at this diagram, okay, if I have 3 points, how many segments that you can get? Okay, so you will get a first segment here, the A1, okay, and also the second segment here, okay, A2. Okay, so meaning that the basic block for the Simpson's 1/3 rule, the number of divisions that you can choose, the n, okay, it must be multiplication of 2. Okay, you need to have at least 2 blocks here. Okay, we will look at it later. What we means that the n must be multiplication of 2 here. Right. Okay, so let me put it in a more general way for the Simpson's 1/3 rule. Okay, so for the Simpson's 1/3 rule, so you will divide the integrations into n segments. Okay, and this n segments is equal width, where the width here is given by h equals to xn minus x0 divided by n, and n must be multiplication of 2. Okay, meaning that it can be 4, 6, 8, 10, and so on. So multiplication of 2. Okay, so the Simpson's 1/3 rule is given by this formula. Okay, so integration from s0 xn yx to dx. Okay, so you have the name 1/3. Okay, so I have 1/3h here. Okay, and inside the bracket, we have the starting point. Why not? Okay, and if you recall back to the trapezoidal rule, you have plus 2y1, 2y2, okay, until 2yn minus 1, and then plus the ending point, right? So this is the trapezoidal rule. Okay, so however, for the rectangular rule, starting point and ending point is the same. You still will have y0 plus yn. Okay, however, for the intermediate value, okay, so previously you have 2, 2, 2, right? 2y1, 2y2 until the 2yn minus 1. So this is for the trapezoidal rule. You have the constant coefficient 2, 2, 2. Okay, but for the Simpson's 1/3 rule, we will have the constant coefficient in the sequence of 4, 2, 4, 2, 4, 2. Okay, so meaning that I will have 4y1 plus 2y2 plus 4y3 plus 2y4 plus until, okay, So this is the second last. Okay. And this is the third last. Okay, yn minus 2. Okay, so my question is, we have 4, 2, 4, 2, 4, 2. So until here, so this shall be 4, 2. Or this shall be 2, 4. All right. Okay, so the answer to this should be 2, 4. Right, because we want it to be in a symmetry form. Okay, so if you start the constant coefficients with 4, 2, so we should also end it up with 2, 4. So only that it will be in symmetry. So you have 4, 2, 4, 2, 4, 2. Then you end with 2, 4. So balance. All right. Okay, so again, I observed that there are some patterns that we can rewrite it in more general way. Okay, so I shall have 1 over 3 h. Okay, and we try to group it according to the constant in front of the y. Okay, so here you have 1y naught, right? And you have 1yn here. So these two shall sit together. So we have y naught plus yn. Okay, and you observe here you have the 4 for y1, 4 for y3, and 4 for y5 here. So meaning that I shall have 4 multiplied to the summation of yi, where my I start from 1 until 1, 3, 5, and so on until n minus 1. Okay, so means the I here shall take the odd number. Okay, and another category from the constant coefficients of 2. So you have a 2y2, 2y4, 2y6, and so on. So meaning that I have 2 multiplied to the summation of yi, where my I shall be 2, 4, 6, and so on until n minus 2. Okay, so the 4 you multiplied to the group for the odd number, I odd number, and the 2 you multiplied to the y for the I for even number. Okay, so you can split the calculations into 3 categories here. So the first category you multiply to 1. The second category for the y odd number, y1, y3, y5, and so on, you multiply to 4. And the third category, when your y is even number, so you have y2, y4, y6, you multiply to 2. Okay, so we will look at it later here. Right? Okay, so this is the equations for the Simpson's 1 over 3. Then now let us look at the Simpson's 3 over 8 before we proceed to the example. Okay, so for the Simpson's 3 over 8, okay, so Simpson's 3 over 8, we are making use of third order polynomial here. Okay, so similarly, if you have a third order polynomial, you know that to get an you try to approximate the functions here by using a third order polynomial. Okay, so to get a third order polynomial, you need to have 4 points, right? So let's say this is the first, second, okay, third, and this is the fourth point. Okay, so let me name it S1, S2, S0, S1, S2, S3. Okay, so you have 4 points. Okay, so if I have 4 points, how many segments here or how many blocks here? So I have the first block, second block, and the third block. So you know that if I want to use Simpson's 3 over 8, Since the basis of the Simpson's 3/8 is we derive the integral by using the third order polynomial. So by using third order polynomial, I need to have 4 points. So 4 points, if I look at this diagram, if I have 4 points, I actually have 3 blocks here. Okay, so this will imply that for the number of segments for the Simpson's 3/8, okay, the n, it must be multiplication of 3 because we are making use of a third order polynomial here. Okay, so means the number of segments that you choose, it shall be 6, 9, 12, 15, and so on. The multiplication of 3. Right. Okay, so for the Simpson's 3/8 rule, okay, the equation will look like this. So you try to find the integration from x naught to xn yx dx. Okay, so it gets the name of Simpson's 3/8. So here I shall have 3/8 h. Okay, so inside the bracket, so similarly, I have the starting point, y naught multiplied to 1. And I have the ending point, yn multiplied to 1. Okay, where inside here, for the trapezoidal, you have intermediate value you multiply to 2. For the Simpson's 1/3, for the intermediate value here, you have the pattern 4, 2, 4, 2, 4, 2 until you end up with 2, 4. Whereas for the Simpson's 3/8, the pattern will be 3, 3, 2. Okay, so you shall have 3y1, 3y2, 2y3, 3, 3, 2. So you have 3y4, 3y5, 2y6. Okay, until you end up with, okay, so this is the second last point, third last point, right? Okay, and this is the fourth last point. Okay, so here I have dot, 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 many intermediate value here. Okay, so similarly, we would like it to in the form of symmetry. So if you start with 3, 3, 2, 3, 3, 2, so we want it to end in the form of 2, 3, 3. All right, so this shall be 2yn minus 3, 3yn minus 2, okay, and 3yn minus 1. Okay, so you try with you start with 3, 3, 2. So you need to finish up it with 2, 3, 3. And the starting point you multiply with 1, and the ending point you multiply to 1. Okay, so this shall be the equation for us to use for the Simpson's 3/8. Okay, so let us summarize all. Right, okay, so I add a slide here. Okay, so to summarize all, okay, so for the rectangular rule, okay, the integration for the yx dx is given by h y0 plus y1 plus y2 until the second last, not the ending point. Right. Okay, whereas for the trapezoidal rule, okay, the integration can be obtained by using 1 over 2h, okay, starting plus ending, and the intermediate you multiply it to 2, so I start from 1 until n minus 1. Okay, so this is the trapezoidal rule. Okay, whereas for the Simpson's 1 over 3 rule, I have the integration is given by 1 over 3h, okay, starting, ending, okay, then I have the 4, okay, multiplied to the odd number, and I have the 2 multiplied to the yi, where the I is the even number, right? And lastly, we have the Simpson's 3 over 8 rule, okay, where the integration of the function, okay, is given by 3 over 8h. Okay, so I have the starting and I have the ending. And for the intermediate terms, we have the pattern 3, 3, 2. Okay, until we end up with 2, minus 1, minus 2. Okay, so this should be minus 3. Okay, 2, 3, 3. Okay, so this is the equation that we can make use for the rectangular rule, trapezoidal rule, Simpson's 1 over 3, and Simpson's 3 over 8. And for the rectangular rule and the trapezoidal rule, n can be any value. Okay, so meaning that you can choose the n to be 9 segments will be okay. Even you want to use it to 4 segments, it is all right. Okay, whereas for the Simpson's 1 over 3 rule, n must be a multiplication of 2. Okay, so meaning that n, you only can have it as even number, so 4, 6, 8, and so on. Okay, whereas for the Simpson's 3 over 8 rule, your n must be a multiplication of 3. So your n shall be 6, 9, 12, 15, 18, and so on. Okay, so this is the summary for the first 4 numerical methods that you have been introduced to. All right. Okay, so now let's proceed to one example here. Okay. All right. So now we want to approximate this. Okay. So now. Okay, so maybe I change this. Okay, so we solve using the rectangular rule and trapezoidal rule first. Okay, so let's say we want to approximate the value of these functions by using first rectangular rule, second trapezoidal rule with suitable number of divisions. So the n you need to determine yourself. All right. Okay, so rectangular rule, trapezoidal rule. Okay, so now let us determine the value of n by ourselves. Okay, so where we will make use of the n. Okay, so you know that n is needed when we want to calculate the h, where the h is actually given by the value of Sn minus S0 over n, right? Okay, so where is the Sn and where is the S0? Okay, so S0 is the lower bound of your integration and Sn is the upper bound of your integration, because in general form we have the S0, Sn, ys, ds. So S0 is 1 and Sn is 4. Okay, so for the rectangular rule, you know that the n, the number of divisions, can be any value. Okay, so let's say I want to choose the n since any value, right? Okay, so let n equals to 4. All right. Okay, so I will have upper bound 4 minus lower bound 1. Okay, divide by n 4. So you have 3 over 4, 0.75. All right, 0.75. Right. Okay, so in this case, n equals to 4 is still a good choice because you get a finite number here. Okay, so let's say now we let n to be 5. Okay, so now I let n to be 5. So you have 4 minus 1 divided by 5. So you have 3 over 5. Right. Okay, so here you get a 0.6. All right, still a good choice if you let n to be 5 because you get a finite value here. All right, n to be, if you choose n to be 6, still okay. How about now we let n to be 7. Okay, if you let n to be 7, so you have 3 over 7 here, right? Okay, so if you calculate 3 over 7, you get 0.428571428 and so on. Okay, if you choose the number of divisions as 7. So this is not a very smart selection. I would not say that this is wrong, but if you choose n equals to 7, if you try to calculate the h here, you get infinite decimal places here. So meaning that this is not a smart choice. Okay, so remember that if you have not been stated what is the suitable number of divisions here, then you just choose the value of n, where you try to calculate for the h, you will get a finite number here. All right. Okay, so for this case, I will just choose my n to be 10. Easier. All right. Okay, so I choose my n to be 10 here. Okay, so now let us calculate the equations here. So firstly, let us proceed to the trapezoidal rule. Okay, so we let n to be 10. All right. And I know that the h can be obtained by using the upper bound of the integral minus the lower bound of the integral divided by the n. Okay, so the question is to solve for, okay, so this is the question. So you want to find for the integration for 1 to 4 x over square x plus 1 dx. Okay, so I know that this is my lower bound and this is my upper bound as n. Okay, so I shall have 4 minus 1 divided by 10. Okay, so you should know that you get a 0.3. All right. Okay, so make sure you choose a suitable value for your n such that here you have a finite decimal places here. Right. Okay, so let us try to solve this by using the trapezoidal rule. Right. Okay, so for the trapezoidal rule, this is what we require, right? Okay, so you need to have the equation of, so I know that for the trapezoidal rule, okay, this is the equations that I have. All right. Okay, so I will prefer to solve it by using table form. Right, so now let us develop the table for the trapezoidal rule. All right. Okay, so for the trapezoidal rule, the table will look like this. Okay, so this shall be the value for xi. Okay, and this shall be the value for the y-x. Right, where the y-x will be the function that you want to integrate. Okay, so you know that you want to integrate from 1 to 4 x over square root x plus 1 dx. Okay, so if I rewrite the general form, okay, so meaning that integration from x naught to xn yx dx. Okay, so if you're comparing these two, so meaning that your y-x actually is the function of x over square root x plus 1. Okay, so I will substitute the function y-x here. Okay, so here will be x over square root x plus 1. All right. Okay, so previously we know that by choosing n equals to 10, you have the step size h equals to 0.3, right? Okay, so meaning that we start from the lower bound, okay, the lower bound, okay, which is 1, okay, then the next step, we just, okay, so the line will be like this, x naught, x1, x2, okay, until xn, okay, where the width here is h. So meaning that for the x1, you just need to plus the h to the x naught. Okay, so if this is 1, so the next point will be 1.3. All right. Okay, so the next point will be 1.6, okay, 1.9, 2.2, okay, 2.5, right? Okay, let me decrease the size of my writing. Right. Okay, so my starting point x naught is 1, and my ending point, I know that the xn is 4. Okay, so meaning that start from 1. The next value, I always increase with h, where the h from previous calculation is 0.3, where we let the n to be 10. Okay, so I have 1.3, 1.6, 1.9, 2.2, 2.5, 2.8, 3.1, 3.4, 3.7, and end up with 4. Right. So from the starting point until the ending point, the increment in between is by h, which is 0.3. And this 0.3 comes from where we let the n to be 10. If you choose the n to be 5 or to be 6 and so on, so here you will have the different step size of h. Okay, so now let me draw some vertical line here. All right. Okay, so what you need to have, Okay, so let me go back to the trapezoidal, so for the rectangular rule. Okay, so for the rectangular rule, right? Why not means the value of y when x is s0, right? Okay, what is y1? Okay, y1 means the value of y when x is s1. Right. Okay, so here, in order to calculate for the rectangular rule, I need to know the value of y when x is 1, when x is 1.3, 1.6, and so on. So meaning that I just need to substitute the x here as 1, 1.3, 1.6, and so on into the functions here. Okay, so this is the calculation will be very quick if you know how to formulate this by using your calculator. Okay, so I have posted the video how can you form the equations in your calculator, so you can refer to that. Okay, so now let us try to formulate this in the calculator, and we try to find out what is the value of the y-x when x takes the value from 1 to the subsequent value. Okay, so I use 4 decimal places here. Okay, so you just need to substitute the value of x here. Okay, the value of x here. Okay, by using 1, 1.3, 1.6, and so on. Okay, so this shall be the answer that you obtain if I do not calculate it wrongly. Right? Okay, and if you observe here, I do not calculate the value for the ending point here. For the xn equals to 4. Because if I'm referring to the equations of the rectangular rule, okay, I will observe that I only need to have the value of y for s0, s1, s2 until the second last ending point, n minus 1, okay, where I do not need to have the value of yn. Okay, so meaning that I do not need to calculate the value for the function y when x is equals to xn. Okay, so that is why in my calculations here, okay, I do not include in the ending point here xn. All right. Okay, so now let us refer back to the equation of the rectangular rule again. Okay, but for the rectangular rule, you need to multiply the h into the summation of y naught, y1, y2 until the yn minus 1. Okay, so therefore, for this one, okay, so I will just add in another row here. Okay, so I add in another row here. Okay, then I put a summation form. Okay, so meaning that I just need to sum up the value here. Okay, I sum up the value here. So this is the value of y naught, y1, okay, until yn minus 1. So I just need to sum up the value here. Okay, then I find out what is the summation here. Okay, so let us sum up the value from y naught, y1 until yn minus 1 here. Okay, I get a 12.5339. Alright, so I hope my calculation is correct. Right? Okay, so lastly, let us substitute the answer that we obtain here into the rectangular rule. Okay, so let me put a box here. Okay, so I know that for the rectangular rule, okay, the integration from s naught to xn yx dx is obtained by using h multiplied to y naught plus y1 plus until the yn minus 1. Right. Okay, so in this way, the integration from 1 to 4 x over square root x plus 1 dx can be obtained by using h. Okay, so h here, we get 0.3 multiplied to the summation from y naught yn until yn minus 1. Okay, where we already obtained it here, which is 12.5339. Right. Okay, so you multiply it to the h, I get a 3.76017. Okay, so if I just leave it in the form of the whatever answer that I obtained here, without rounding it to 4 decimal places. Right. Okay, so this is the answer that we obtain for the rectangular rule. Fine. Right. Okay, so I hope my calculation is correct. Okay, so you try to finish up the calculations. I make the attendance. Or you can scan your QR code. Right. Okay, so apa yang ada masalah ambil attendance nanti tinggalkan nama dekat dekat Google Meet tu. Okay, so I would like to proceed to the calculations.
Ma'am?
Yeah. Nanti tinggalkan nama kat Google Classroom. Okay.
Alright.
Alright. Okay, so this is the calculations for the trapezoidal for the rectangular rule. So now let us proceed to part B here. Okay, so for part B, we want to calculate the integration again, but by using the trapezoidal rule. Right. Okay, so we recall back what is the equations for the trapezoidal rule. Okay, so for the trapezoidal rule, S naught integrate S naught xn ys dx. Okay, we have h over 2 or 1 over 2h. Okay, then here you have y naught, yn, and here you have the intermediate value for the yi. Then for I start from 1 until n minus 1, you multiply with 2. Okay, so this is the equations for the trapezoidal rule. So we are now solving the same question, but now by using the trapezoidal rule. Right. Okay, so if you observe here, we can actually split it into two categories. The first category is those with the constant coefficients 1. Okay, And the second category is those with the constant coefficient 2. Okay, so we will try to change the table afterwards such that our calculations will be easier. Okay, so I would like you to notice here. So from the equations of the trapezoidal rule, so we can have the first category, we multiply it with 1. Okay, the constant here is 1. Okay, and the second category where we will multiply it with 2. So we have the constant coefficients here as 2. Right. Okay, so now the question say that we can use suitable number of divisions. Okay, so previously we let the n to be 10. Okay, so now we can choose another value for the n. Okay, so maybe I would like to let my n to be 6, because the lesser n that I choose, the less calculations that I need to perform. So I'm already getting lazy. All right. Okay, so I choose n to be 6 because I know that this is quite a smart choice. Okay, because when n is 6, my h can be obtained by using Sn minus S naught over n, right? Okay, so I know that the integration is from 1 to 4. So I have 4 minus 1 here. Okay, and I let my n to be 6. Okay, so I have 3 over 6. So I get 0.5, a very good number here. Okay, a smart choice if I choose my n to be 6 because I get a 0.5 here, which is even easier to calculate than the 0.3 previously when we let the n to be 10. Right, okay, so bear in mind, you need to be a very smart person or very clever person in order to determine the value for your n. Okay, so for the rectangular rule, we choose n to be 10, then we get the h to be 0.3. So for the trapezoidal rule, we just try a new number for the n, we let it to be 6, then we get the h to be 0.5. Right? Okay, so now let us proceed the calculations for the trapezoidal rule here. Okay, so similarly, okay, this is the integration that we want to solve. 1 to 4 x over square root x plus 1 dx. Okay, so we will have the same table, the xi. Okay, and here will be the function that we want to integrate. Okay, so we want to integrate the function x over square root x plus 1 here. Okay, so I put it as the header of the table. Okay, and we start from the lower bound here, which is 1. Okay, and previously we know that if I let my n to be 6, my h I get a 0.5. Okay, so means that every subsequent value of x we just plus 0.5. Okay, so I have 1.5, and I have 2, I have 2.5, I have 3, I have 3.5, and I have a 4 here. Okay, so start from the lower bound. Every subsequent value you plus the h until it reaches the upper bound of 4 here. All right. Okay, so let me draw the horizontal line first. Right. Okay, and I know that I need to calculate the value of y when x is 1, 1.5, 2, and 2.5, right? Substitute into here. Okay, but however, before I substitute the value here, I want to make my calculation easier. Okay, so I would like to separate it into 2 different categories here. Okay, so if you refer back to the equations of the trapezoidal rule, Okay, we can split it into two categories. So the first category is the y naught and the yn. Okay, so the starting point and the ending point, right? Whereas the intermediate values between the starting and the ending point, we will multiply it with 2, right? Right. Okay, so therefore, I will separate my table in this way, right? So this is the starting point. Why not, right? Okay, and this is the ending point. Yn. Right, so I will put them in the same columns. Okay, whereas for the values in between y naught and yn, so for example, the y1, y2 until the yn minus 1, we put it in another columns. So this will make our calculations easier because I know that for the first group consists of the y naught and yn, they have the same constant 1. And whereas for the values in between y naught and yn, I know that I have to sum up, then I multiply it by 2. Okay, so before I do the calculations, I just separate it directly. All right. Okay, so I put a tick here so such that I won't do the mistake. So I need to fill up the value of y naught here, yn here, and others than y naught and yns, I need to fill in the value of the y at the second column. Right. Okay, so now you try to find out what is the value of your y when you substitute x as 1, x as 1.5, x as 2, and so on. Okay, so the calculation will be faster if you are able to formulate this function in your calculator. Okay, so I formulate this in my calculator first. Okay, then let us find what's the value here. Right. Okay. So I hope my calculation is correct. Right. Okay, so now what we need to do now. Okay, so I will put the summations form here. Right. Okay, then I sum up the value in these two columns separately. Right. Okay, so you sum up the y naught to yn. Okay, so we get 2.496. Then I sum out those y1, y2 until the yn minus 1. So I get 6.5896. Okay, so if I separate in this way, so this will make our calculations easier. All right, fine. Okay, so now let us look at subsequent steps for us to finish up for the trapezoidal rule. Okay, so I need n box here. Right? Okay, so let me write down for the equations for the trapezoidal rule. Okay, so for integration from x0 to xn yx dx for the trapezoidal rule, we have 1 over 2h, okay, y0 plus yn plus 2 multiplied to the summation yi, I from 1 until n minus 1. Okay, so this is the equation for the trapezoidal rule. Okay, so now let's apply this to the problems that we want to solve. Okay, so for this question, we want to solve for the integration from 1 to 4, where the y-axis is x over square root x plus 1 dx. Okay, so I have a 1 over 2 here. And I know that by choosing n equals to 6, I get h is 0.5. Okay, so here I have a 0.5. Right? Okay, so let me make my handwriting smaller. Okay, so I have 1 over 2 h. Right. Okay. 0.5. And here I have the y0 plus yn. Right. And you know that the y0 plus yn we already find from the summations here. 2.496 indeed is the answer where we sum up the first value for the y and the ending value of the y here. y0 plus yn. The first and the last value. Okay, so meaning that we can substitute the y0 plus yn here as 2.496. Right? Okay, so y0 plus yn is 2.496. Okay, so how about this? Okay, so the summation of yi when I from 1 to n minus 1 actually is the value here. Right, the summation where we sum up those values in between y0 and yn. Okay, so this is the summation of the intermediate value here. So we get a 6.5896. Right. And I know that for the y0 plus yn, we need to multiply it with 1. Okay, multiply it with 1, so we do not write it out. Okay, whereas for the summation of the intermediate value from y1 until yn minus 1, you need to multiply it with 2. Okay, so therefore here I will put a plus 2 multiplied to the summation of the intermediate value here. All right. Okay, so now what you need to do is just calculate it in by using a calculator. Okay, so I get a 3.9188. Okay, so I hope that my calculation is correct. Right. Okay, so the summation of yi the intermediate value is given by the 3.5896, where we already separate out here. Okay, so this is the reason why I separate it into two columns straight away. So this is to make the calculations easier here. Right. Okay, so this is the solutions for the trapezoidal rule. Right. Okay, so any question? All right. Okay, so right. So any question? Already 3 p. Almost 4. Right. Okay. So if there's no question here, then we will stop our class. Then I will see you on Thursday morning. So we continue with one example for the Simpsons. Then we will proceed to the Gauss quadrature. All right. Okay, so we will end our class here. So thank you. So I will take your attendance here. Okay, so Peter. Okay, high count. Okay, Paris. Okay, Siva. Kaizuran. Kevin. Alright, Kevin dah. Ledin sudah. Okay, Amal Hakim tak ada. Amal Hakim. Okay, and Faris tak ada. Alright, Umar tak ada. Wan Muhammad tak ada. Alright. Okay, so see you on Thursday morning.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.